Hello everybody and welcome to my 16th video. This is on the Quine-McCluskey procedure and it's an alternative to the Quine method. I'm going to be presenting a binary version and a ternary version. So here we'll start off with a binary version. Here is a binary function of 4 variables a, b, c and d. The function f here, and here we have the count of n, which is the decimal equivalent of the binary counts. For example, 13 would be 1 times 1 plus 0 times 2 plus 1 times 4 plus 1 times 8. So 8 plus 4 plus 1 is 13. Right, let's get to it. We're going to start off with a sum of products expression for f, and what we do here is we list all the values for which f is a logic 1. So here we can go back, say for here n is 3, d is 0, c is 0, b is 1 and a is 1. Here 3, d is 0, c is 0, b is 1 and a is 1 and f is a 1. So we list all the values of n and d, c, b and a for which f is a logic 1. So we've got 3, 4, 5, 6, 8 and 12 here. And what we do is we combine them into smaller variables by cancelling out. For example, 3 and 1 here, this is 1, these are the don't care states for which f is equals an x, a don't care state. So we're combining 3 and 1 here, and we basically look for the similar values except for one variable where b, for example, is a 0 and a 1. So you match up the DC and the A, and B varies by a 0 or a 1. So here D is a 0, C is a 0 and A is a 1 in all these cases, but B differs by a 0 and a 1 here, so that is a dash. That is, you've deleted the variable. So you combine 3 and 1 in this manner. For example, 4 and 5 here, a bit easier to see. D is a 0 for 4 and 5, C is a 1 for 4 and 5, B is a 0 for 4 and 5, and A is a 0 and a 1. So there's your zeros, there's your ones, there, 0, 1, 0 for B, and A cancels out into a dash. Okay, so you do this for the logic ones and the don't care states as many times as you can, but you don't repeat. You may repeat variables, but you only list them once. So some combinations may give the same reduction, but you only list them once. So what we do then is for all the values of n that we've listed here, we check once you've combined it into a smaller variable, smaller expression say, you place a check mark against each one you've done, and only the unchecked marks get to go to the next stage of the procedure. So here we're dealing with the 1, so logic state here, for example, a 0 is not x and a 1 is x. So we'll go to the next stage. So here are all the values of n for which f is a 1, 3, 4, 5, 6, 8 and 12. And these are the variables. For example, if we go back, D, C and A is a 1, so that's A. C is a 0, so that's not C, and D is a 0, so that's not D. And you're doing a sum of products, so it's a product term So this 3 and 1 is A, not C and not D, and it covers the variable 3. ACD covers the value 3 of 1, but 1 isn't listed. 1 is a don't care state, so you don't list it in the table. So you just place an X to indicate that it covers n equals 3. So you do that for all the unchecked marks, unchecked variables, and you produce what's called a prime implicant table. Now there's something called an essential prime implicant, in which there is only one X in a column for a variable, and this is called a prime implicant, and you denote it with a star. You can see here there's only one X in this column, so that's a prime implicant, and here there's only one X in that. Well, I'll explain later. If you put an X next to the prime implicants which are covered, for example, this X and this X is covered by there and there, so you can delete that, and this X is covered by this, so you can delete that. And if you do that, then this becomes a prime implicant, because there's only one X in that column with that deleted. So the idea is to cover all the numbers of n, variable n, with an X. So 3 is covered by there, 4 is covered by there, and 6, and 8 and 12 is covered by A, B, C, D. So there's only 5 which hasn't been covered. So you've got a choice. You've got either A and not B and not D, or A and C, not B and C and D. So you just list both the possibilities. So you've got the prime implicants there, here, and one with B, C, D in, and one with A, not B, not D in. So F equals A and not C and not D, or A and C and not D, or A and not B and D, or not B and C and D, or F equals A and not C not D, or A and C and not D, or A and not B and D, or A and B and not D. So there's your two. If you draw a Quine map, you'll get the same result. Hopefully you will anyway. I'm going to do a product of sums expression for the same function. Same function f. And this time we're going to concentrate on the logic zeros. So here we have the values of n for which f equals a 0, and again you're looking at the logic. It's the same procedure. You combine, say for example 0 and 2 here. You look for the common variable, except where it differs by a 0 and a 1, so you're doing it in groups of 2. So, for example, this combination here, 0, 2, D is a 0, C is a 0, A is a 0, and B is a 0, a 1, so that's a dash. And the don't care states are listed as well. And you have to say you don't include purely don't care states in the table, prime implicant table. You only include these that have been combined with prime don't care states, logic zeros and don't care states, but not just purely these. Right, so you do this as many times as you can, combine. For example here, 10, 11, 14, 15 have been further combined. 10, 11, 14, 15. There's a 1 there, and a 1 there, a dash there, and a 0, and a 1 there. So that's a dash. So you've already got a dash there. You match the dashes up. match the zeros up, you match the ones up. And you look for a 0 and a 1. So that's C with a 0 and a 1. So you've got 1 dash, 1 dash, for example, for 10, 11, 14, 15. So then, because you're looking at logic zeros, logic state 0 as a variable x, and logic state 1 as a variable not x. So, list the prime implicant table, which is the same as before, but the terms are all together. You're looking at a product of sums. Yeah, products of sums. So we're ORing the terms together. Here is the values of n for which f equals a 0 here across the top. And again, for example, what can we do? Oh yeah. This is D, D is a 0, so that's D, C is a 0, so that's C, and A is a 0, so that's A, and B is cancelled out, so that becomes A or C or D. And it has the value of 0, 2 there, in here. 0, 2 for n. So 0, 2 here. So we'll list these, all the implicants here, for which the unchecked marks. Go through it again. All the unchecked ones here are included in the prime implicant table, so there's 6 of them. Yeah, so same again, A, B, A or C or D, B or C or D, A or not B, or C, not A or B, or not C, not B or not D, not A or not D. So these, you place a check mark for which n is covered by this variable term, and an essential prime implicant again is one where there's only 1x in the column. So here there's 1x here, here there's 1x here, and here there's 1x here. So these 3 are essential prime implicants and that marked with a star. Here, if you delete this one and this one, well, if you delete this one because it's covered by A or C or D, this becomes an essential prime implicant. And if you delete this one because this x is covered by this x and this x is covered by not B or not D, then this becomes an essential prime implicant, and you can delete these 2. So everything is covered by the essential prime implicants 0, 2, 7, 10, 11, 14, 15 there, and 13 there. So every essential prime implicant is included in the expression for f. So f equals A or C or D, and A or not B or not C, and not B or not D, and A or not D. Right. So that's, if you drew a Quine map, that's probably what you would get. Well, that is what the expression you would get from a Quine map. Now we're going to go through the Quine-McCluskey procedure in ternary. This is I'm using the algebra, the ternary algebra, in my video, a ternary algebra with 6 binary operators, which I believe is my 13th video, I think. So we'll go through what happens here. So basically we have a three variable ternary function a, b, c and f. I've labelled n for the decimal count of the ternary variables. So for example 15 will be 0 times 1 plus 2 times 3 plus 1 times 9. So 9 plus 6 is 15. I'm using the coding F0 and F2 for f. So if f is a 0, f0 is a 0, f2 is a redundant state. If f is a 1, f0 is a 1 and f2 is a 1. If f is a 2, f0 is a 1 and f2 is a 2. And if f is a don't care state by an x, f0 and f2 are both redundant states or don't care states. So I've just labelled them R to differentiate between f, a don't care state in f, and a don't care state in f0 and f2. So we apply the coding f0 and f2 to f, and we're going to first start off with f2 then f0. So let's get to it. So here's the values for f2. These are the values of n for which f2 is a logic 2. And basically, can we find an easy one to do? 0, 9 and 18. 0, 9 and 18. So basically, you combine them in groups of 3. So 0, 9 and 18 here. C cancels out, B is a 0 and A is a 0. So I'll show you how you do that. 0, 9 and 18. 0, 9 and 18. B is a 0 there. A is a 0 in every case there. But C varies by 0, 1 and 2. So if you get a 0, 1 and a 2, you can cancel it out. So this reduces to A is 0 and B is 0. And you do that. These are the redundant states for which f is redundant, f2 is redundant. So these are the values of n. These are the values of the logic states for the redundant states. And you combine the lower ones into higher ones here and again here. So you're cancelling out variables. So here these are 2 variables and this is a 1 variable. Here these are 3 variables and this is a 2 variable. So once you cancel them out, so here we're going to do this cancel out again to get b equals 2. So that's 24, 6, 15, 25, 7, 16, 26 and 8 and that's 17. So 24, 6, 24, 25, 26, where are we? We got 24, 25, 26, which is this line here. 6, 7, 8, which is this line here. This is a redundant state. And 15, 16, 17, which is this. So we're the 2, there's a 0, 1 and a 2 there. A 2 there and a dash there. So that cancels out. The C cancels a dash. The A is already a dash and B is a 2 in all 3 cases. So that cancels out and there's no further reductions you can do. So we'll go to the prime implicant table again. So here, if the logic state is a 0, the variable is x minus, which is x plus 2 modulo 3. Or if the logic state is a 1, it's x plus, which is x plus 1 modulo 3. And if the logic state is a 2, the variable is x. So here we have the prime implicant table again, and we list the values of n for which f2 equals a logic 2 across the top, and x for which the term covers the value of n. So for example, 0, 9 and 18 here. B's are 0 and A's are 0 and C cancels out. So if it's a 0 it's x minus, so that's A minus and B minus, and it covers the values of 0, 9 and 18. So you do that for all the variables, and you're using the minimum function, which I've called the 0 function here. Now, the essential prime implicants are marked with a star, and some of them are non-essential because they're repeated, so you can delete them. For example, this line here, this x is covered by this x here, and this x is covered by this x here, and this x is covered by this x here. So you can delete those 3 terms, and then you're left with the essential prime implicants, because that has only one x in there, and that has only one x there. So you do that, and you choose the minimum coverage. So we've only got these a choice of 4, because this is covered 0, 9, 18. This is covered 12, and this is covered 24, 25, 26. So there's only 4 I haven't covered. So you've got a choice. All those prime implicants there, plus A plus 0B plus, which is there, and or alternatively, all these prime implicants here, plus B plus 0C minus, which is here. So you've got a choice. F2 equals B2 squared A minus 0B minus 2 squared A minus 0C minus 2 squared A plus 0B plus 2 squared 1. You're adding a constant logic state to the expression. Or F2 equals B2 squared A minus 0B minus 2 squared A minus 0C plus 2 squared B plus 0C minus 2 squared 1. So you've got these differ, so you've got 2 alternatives. Okay. Here we're going to go through the logic zeros of F0. So we'll list the values of n for which F0 is a 0. So this is n 6. So for that combination, F0 would be a 0, etc. And again, we combine variables into smaller variables. These are redundant states for which F0 equals an R, 3, 5, 13, 22. And for example, here we've combined 6, 7 and 8, so 6, 7, 8 here. So C is a 0 there in all 3 cases, B is a 2 in all 3 cases, and A differs by 0, 1 and 2. So C is a 0 there, B is a 2 there, and A cancels out because it's a 0, 1 and 2. So you do that for as many variables as you can, and only the unchecked marks go into the prime implicant table. So here we have the prime implicant table. Shove that over across. So here, if the logic state is a 0, the variable is x. If the logic state is a 1, it's x minus, which is x plus 2 modulo 3. And if the logic state is a 2, it's x plus, so the variable is x plus 1 modulo 3. So here is a prime implicant table. These are the value of n for which F0 equals a 0. And, for example, if we take this expression here, 0, C is a 0 and B is a 2, and A cancels out. So C is a 0, which is a variable x, B is a 2, so it's B plus, and it's B plus 2 squared C, and it covers the values of 6, 7 and 8. So this is how you generate the table, and you can see that each variable term has one x in each column, so they're all essential prime implicants. So there's only one real answer for f0. It's a minus 2 squared b 2 squared c plus 0a plus 2 squared b 2 squared c, 0b plus 2 squared c, 0b plus 2 squared c minus 0, 1, adding a constant logic state to the expression. And f equals f0, 0 squared f2. So this is f0, and we've done f2 previously. So these two expressions are connected together by the 0 squared function. Right, I think that concludes the presentation. I hope you've enjoyed it. Thanks for watching. Bye.